So now we have this reaction, and this reaction is at equilibrium, and at equilibrium we have this concentrations for these three species. What happens when we come along and dump one of the three, such as let's say we come along and add more iodine gas inside this closed sealed container and then seal it back so that none can escape. Suddenly the concentration of I2 goes up. If the concentration of I2 goes up, it will not be 1.72 molar anymore, but it will be some other number, larger number. But then if you were to evaluate this expression with something else, where instead of 1.72 here you have some other number, a larger number, the final outcome will not be 1.0 times 10 to the 1, it will be a larger value. But that is not an equilibrium value. For this reaction, it turns out that at a given temperature, whatever that temperature is, the equilibrium value, it's a constant, and that constant must evaluate to this value. If it's going to be some other concentration for our reactant or our product, it must still evaluate to the same value. No matter what the final composition is, it must evaluate to the same value. So how do we deal with that situation? What happens when we introduce some product or some reactant? What happens is that we are stressing the system. The system that is at equilibrium, once we introduce a stress to that system which is nicely balanced, it's going to cause an alteration in the concentrations of the species in such a way that we come back to equilibrium. We will re-establish equilibrium. So in this case, if I was to add some iodine here, raising its concentration, what will happen is, if nothing was to happen, then the number value will go up, meaning the product term here increases while the reactant term remains the same. In order to bring us back to equilibrium and evaluate back to this value, some of the some of the iodine that we have added will be consumed together with hydrogen gas, and more of this reactant will form, and the product amounts will go down. As those amounts go down and this amount goes up slightly, we will adjust it to the point that we come back to the equilibrium. That's what this equilibrium system will do. So whenever we add a product in a reaction that's at equilibrium, the system will act in such a way to counter that stress. So if I added a product, in order to counter that stress, product will be consumed. If I added some reactant to a system at equilibrium, then in order to counter that stress, the reactant will be consumed. So if you were to add ammonia to this reaction, it causes a stress to the system, and to relieve that stress, added ammonia as much as possible will be consumed so that we go back to our equilibrium value. Similarly, if nitrogen or hydrogen was added, it will be consumed. Now, does it mean all of it will be consumed? No. It depends on how we come back to the equilibrium. Whenever we evaluate the equilibrium expression, it could get fairly complicated with many terms involved, and some of those raised to some exponent. So as long as we come back to our original value, the system will only move up to that point. So that means that we can easily find out what happens to a system that's at equilibrium when suddenly the concentration of one of the reactants or product changes. The system will move in the opposite direction of the equation from where some stress has been added. This doesn't just apply to solutions that are colorless, but we can actually witness this in colored solution. For example, iron isothiocyanate given here establishes equilibrium between iron aqueous and isothiocyanate here. Now in this equilibrium, iron isothiocyanate FeSCN2+ is red in color and iron is yellow in color. these are the three different versions of the system at equilibrium. The first one, and then uh, shift to reactant with more red color. So if we were to come along and add some product, maybe iron, maybe just SCN minus, that would cause the system to move more to the left, and we can see that the new equilibrium has higher concentration of this compound rather than iron. If we were to come along and add more of this, the system will actually move to the right, consuming the added iron isothiocyanate, producing iron which is yellow in color. Not only can we stress the system by adding some component, but we can also stress the system by removing some component. So if we could remove this, the system will still move to the right. If we remove this, the system will move to the left to re-establish equilibrium. Equilibrium is also present in endothermic and exothermic reactions where heat is involved. For example, this is an example of an exothermic reaction where we write down the heat as a product in an exothermic reaction. What happens when you change the temperature at which you carry out this reaction? What happens when you carry out this reaction at a high temperature? High temperature is equivalent to adding heat to a reaction, and heat is already a product of this reaction. So if I carry out this reaction at a high temperature, I'm effectively dumping more of one of the products, meaning that the system will try to counter this according to last Chateliers principle, and it will counter it by moving in the opposite direction. So at higher temperature I will get more hydrogen gas and more nitrogen gas. What if I try to carry out this reaction at a low temperature? At a low temperature, we are effectively removing this product, and if we are to remove this product, the system will counter by forming more of that product. Hence the system will move to the right side of the reaction. So exothermic and endothermic reactions can be monitored that way, and we can even find out if a reaction is endothermic or exothermic if we know which side the system moved by raising the temperature or lowering the temperature. So in this case, this is an exothermic reaction. If I raise the temperature, the system moves to the left. If I lower the temperature, the system moves to the right, telling me this is an exothermic reaction. In this case, if I raise the temperature, the system moves to the right, because higher heat is actually increasing one of the reactants, so the system moves to the right. If I lower the temperature, that means I remove heat, then the system moves to the left. Finally, pressures. Since it's either concentrations or pressures that are involved in an equilibrium expression, what happens when the pressures of gases change? What happens when I have a reaction that's completely based on pressure but not aqueous? Well, think of it as if it's aqueous because the effect is the same. Increasing the pressure of one of the gases is going to move the equilibrium similarly to how we saw it with aqueous reactions. But here you have to be careful. For example, if we were to increase pressure here by decreasing the volume, for example, well, which side will the reaction move? If we lower the volume in which this reaction is taking place in some sealed container, we further lower the volume, the reaction will move to the right. The reason is, look at the concentrations or look at the pressure. We have 4 moles of reactants, 3 plus 1, nitrogen is 1 mole, and only 2 moles of the product. If we are going to decrease the volume, that means the pressure is going up. The system will try to counter that pressure increase, and so the system will try to go in the direction which gives you less number of moles of a gas, which would result in less pressure. So in this case, the system will move to the right when the volume is decreased. What if I suddenly increase the space, suddenly increase the volume? Which side will the system move? In that case, the system will move to the left, because there was sudden drop in the pressure and at equilibrium the system should have higher pressure, so it will try to counter my uh, decrease in pressure by increasing the volume by moving the system to the left. And lastly, catalyst has no effect on equilibrium. A catalyst only speeds up the forward reaction and the reverse reaction at the same time. So the only thing that happens with the catalyst is that we come to equilibrium much faster than we would have otherwise.